Alright, hello everyone. We're going to be talking about climate change and why it's important, the impacts, and really just trying to understand climate change and really kind of bring the argument to people and kind of show them what the science is and the arguments for it really is climate change from a meteorologist, atmospheric scientist like me. Just recently graduated, so the knowledge is still fresh in my mind, and people, I'm sure, would rather hear this from a scientist on climate change. Really, someone who's done, looked at papers and done research and a lot of schooling on this than maybe a politician who just sees it as another issue. So that's kind of what I'm talking about, and you see, I say why it's complicated. The reason it's complicated is really because of the photo, right? Politics has really gone in the way of a lot of climate science advancements and really trying to solve problems within climate change. And but there's not a lot of disagreement. 97% of climate scientists believe and agree that climate change is human caused and not just solely from natural variability. The other 3% have an argument, which I will get into in the future. Now, first is the basics. One must ask, what really is climate change? Well, it's two different words. Climate, first of all, is this historical decadal averages of meteorological conditions. So, for example, in California, you got hot and dry summers, cool and wet winters, and we won't talk about why. We'll talk about that in the meteorology presentation I'll be giving. But the reason is because of the global circulations around the Earth kind of allows for this system that we have in California, but that's climate related. The average, the decadal averages, weather is more of some your day to day changes in this in climate variability. Climate change itself is defined as deviations from the mean of climate, and is a trend and details how climate conditions on Earth may be changing. Climate change is affected by both natural and human-induced variability, which I mentioned at the start, and that's my definition. The official IPCC definition, which is the Intergovernmental Panel on Climate Change. This is when every government from the UN comes out and they make an agreement on a statement on climate change. They make a report every few years or so. I think it's 5 to 7 years. Maybe it's more frequent. No, I think it's 5 to 7 years. I think they made one just the past year or so. But their most recent definition is climate change refers to a change in the state of the climate that can be identified by using statistical tests, for example, by changes in the mean and or variability of its properties that persist for an extended period, typically decades or longer. Climate change may be due to natural internal processes or external forces such as modulations of the solar cycle, which we'll get into later, volcanic eruptions, which I don't cover but important, and persistent anthropogenic, which is the human-induced, changes in the composition of the atmosphere or in land use. So here on the right, I hope you can see my cursor, but this is Hurricane Beryl. It took me a minute to even remember what it was, but it's Beryl, and the reason I put it here is because it was the earliest Category 5 on record. So, very cool hurricane just this past year, and I could have put Helene there as well. We've had pretty interesting hurricane season this year. Now, first, let's look at the natural variability. Before we get into the human-induced stuff, we gotta really understand natural variability, because this is how the Earth's climate has changed over 99.99% of its history. And no, I'm not talking about killing germs here. I'm talking about Earth's history with that 0.99. Or unless you can count humans as anyway. So the climate has actually changed substantially, even more than now. It's changed pretty largely. We've had days on Earth when it was first formed. It was just a hot ball with no oxygen, no life. I think I say here, it was like hell on Earth. It basically was. And eventually, the planet began to cool from just favorable conditions, and the sun wasn't really hot enough. There wasn't as much of an atmosphere to hold this heat, so it started to cool. Now, The exact reason as to why is unknown. I think it could have to do with the moon like hitting the Earth or something, maybe ripping part of its atmosphere. I don't know too much. The Earth might have had a thicker atmosphere. Maybe that was why it was warmer. I don't exactly know, but there were no oceans back then either. But eventually, there was water that made it to Earth, and and a lot of CO2 and water. You started to get life, bacteria, that led to plants, that led to oxygen on Earth, that led to organisms, that led to us, essentially. And this organism boom, as I call it, has currently been past half billion, maybe a billion at the far end years or so. And this snowball Earth kind of occurred during the start of that boom. This kind of slowed the boom, I guess you would say. 600 million years ago, there was snowball Earth, which, ironically, right, I was just talking about this hot ball of Earth, and now I'm talking about the snowed Earth. It's completely covered in ice. Even the equator had a layer of ice on it, but I don't believe it was year round. I couldn't find any good source to prove it. We just know that it was covered in ice. I mean, it was so long ago. The geological record is hard to get it very precisely, but yeah. So we've had some big variations. Right? Look, Earth doesn't look like that anymore, does it? Now we have the warm period. We're progressively getting closer and closer to today. This is 50 to 60 million years ago, and this is when Earth entered its most recent very warm period. Temperatures were more than 20 degrees Celsius above today's temperatures, or I guess, is that what that is? Relative to today, yeah. Relative to today, um, and that's very, very warm. I think the P stands for some era. This is from my old lecture notes. I didn't put what the P says, but it's a very warm period, and it didn't last too long, maybe like a million years, but it was so hot that my climate change professor, he also taught atmospheric chemistry, so I wrote atmospheric chemistry. He called it having alligators in the Arctic because the global temperatures were so warm. Yeah, so the global average temperature today is about 15, 16 degrees C. That means that temperature then was about 35 degrees C, which is 95 Fahrenheit, which, yeah, I could understand having alligators in the Arctic with that temperature, but a lot of people will argue, the Earth was so warm back then, why should we care now? And, well, there aren't alligators in the Arctic currently. That's the first thing. Now, even more recent stuff. This is the past 800,000 years, which is how far the ice core data goes. So this is data from ice cores. Now we're talking about proxy measurements. Before, we were looking at geological, like rocks, what rocks told us, rock formations about the climate. But now these proxy measurements of the ice cores are much better at giving us an idea of what the climate may have looked like. They're much better they're much better at showing us what things looked like, because this is actually looking at we'll talk about it in the next slide. But as I said, we used to use fossils and rocks for really old climate data, more than a million years old. And there's other proxies that we looked at. We'll talk about later, like tree rings. But this is a really interesting graph. We see that there's a general oscillation here between ice age, interglacial periods, and the last glacial period, I think, was 20,000, 10,000 years ago, which you can see way down here at the bottom, and then we rise back up. So right here, there's an ice age. So we have interglacial, ice age, 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 interglacial. So we were already actually in an interglacial before. See, this is where we are. Oops, go back. So this is where we were before the anthropogenic human-caused CO2, and this is where we are now. So we were already in a interglacial period before we did this, and this is the ppm. So is that about 280? See, its peak is around the same. In the interglacial periods, and it's about 182 or so. In the glacial periods, I think about 210. It's actually 180. I'll have to edit that in the slides. If you want these slides, I can post them in like a Google Drive if you're curious. But yeah, and yeah, that's CO2, and then here's the temperature, actual temperature variations, and we actually haven't faced a proportionate temperature increase to the amount of CO2 increase because there's a time lag and a lot of feedbacks that haven't yet occurred, which we'll talk about later more about that stuff. And now is the very recent variability. This is on human time scales. Now we're talking, and this is the last ice age we've zoomed in now, right here. So average, and this was the little ice age down here, I believe. Yeah, this was the little ice age. And then, wow, look at us now. We're just on a rocket. Yeah. So this is the past like 200 years from industrial revolution, right? CO2 that we're pumping out, and that's not normal. We haven't seen anything like that, through all these graphs except for this one. But that was kind of a one-off thing. And this is actually even faster than this, because remember this. Look at the axes on the graph. This is millions of years ago. This is 10 million years. So this is like this thin part is like 1 million years. This is 100 years, 1 degree C. So this is actually warming much faster than even the 20 degree C one, and that doesn't include tipping points, which we're going to talk about later as well. There's a lot of climate stuff. That's why I said it's complicated. Yeah, we usually establish a baseline. It's either 1750 or 1850. Very common because that's when the Industrial Revolution started, and we like to look at emissions since the Industrial Revolution because that's when we started putting all this CO2 into the atmosphere. Another common baseline is 1900 because it's the start of the 20th century, and it's really when we started putting more and more CO2 into the atmosphere. And that's what this one is. This is a temperature anomaly based on the 1900 anomaly. As you can see, almost 1.5 degrees C, really. This is about 1 degree C from 1900 temperatures. So this is a graph I made. I actually made that one. And then this is the one put out by NOAA. Carbon dioxide is at about 420, methane's at 1922, nitrous oxide is about 337. And this is, and it also tells you how it compares to pre-industrial, which we talked about was about 1750, 1850, depending on who you ask, really. And 50% higher for CO2, 166% higher for methane. We emit a lot of methane. And nitrous oxide at 25% higher than normal. These are all greenhouse gases. These aren't all of the greenhouse gases. You also have you have CFCs, which are really bad. Greenhouse gas, which I don't really talk about that much, briefly later on CFCs, but there's also what's the other one? Sulfur hexafluoride, which is the worst greenhouse gas of them all. I think it's like 30. It's like 1630. I don't know. It's like 30,000 times worse than CO2. It's like so bad. It's like 30,000 times worse. It's really, really bad. And people use it to make their voice sound deep, and I'm like, no, don't use it at all. Alright, so we're back on the proxies. I probably should have rearranged stuff, but so on ice cores, this is an example of one. This is a really small ice core. The really old ice cores go really deep into the earth. And the deeper the ice core, the older the data is, the older the formation of the ice is. And we kind of know that if you ever took Earth science, you remember that the further you go into the Earth's crust. So that's why the older ice formations are going to be at the bottom, and the newer formations will be on the top. So the Earth has its own natural stack that it makes if you into data structures, about stacks. That's kind of what the Earth does. Let's see. So what climate scientists do is they take the ice core and they extract the air bubbles, which give you the levels of CO2, oxygen, and methane at the time that the air was trapped in the formation of the ice, because That's what they're getting. They're getting air that was trapped in the ice when it formed, however many years ago. And how many years ago? Actually, I don't exactly know how they figured that out, but there could be some carbon dating or something going on, probably. Carbon dating doesn't go that far back, but something similar process. Um, yeah, and they can get temperature from this as well, right? Because this was the graph from Antarctica ice cores. And I don't know if this is Antarctica or Greenland, because they also take Greenland ice cores as well, but it's one of those two. And the Antarctica ones go further back because Antarctica's existed longer. Its ice is older and it's been there longer, so Antarctica is better for climate change, I guess. Because climate change is global, so it doesn't really matter where you take the measurements. All right, now we have tree rings, which is a more modern thing. I say modern, but as in like you can only go back a couple thousand years, whereas ice cores you can go back almost 1 million. Trees, yeah, they tell you a lot about it. They tell you about the age of the tree, how many rings there are, which is true, but it turns out the thickness of each individual line kind of tells you about the weather conditions, if they were more or less favorable for the growth. So yeah, the thinner spots are more drought areas and just overall areas where the tree was less favorable conditions. And I can tell you about the CO2, the temperature, precipitation amounts, and this data is, we kind of rely on tree rings as well. Up until about the last 300 years or so, there was obviously technological boom, which we kind of mentioned before, right, with the Industrial Revolution. Yeah, that's when we started taking weather, meteorological measurements, temperature, probably humidity, pressure, through barometers, right, and wind. And 400 years ago is really when we started getting more established records from measurements, human. Like we take the measurements like we do today. And obviously the accuracy has increased in recent years with the invention of satellites and more advanced sensors that we will look at later. So next up is the Milankovitch cycles. These are natural variability still. We're still on the subject of that. First we have obliquity, which is the tilt of the Earth, which varies by a few degrees. I don't know. It's between like 23 and a half. It varies between like 22 and like 26 or something. I don't know. We're kind of like in the middle. I know that. We're like in the middle. But it varies by a few degrees every 40,000 years. This variation of the tilt leads to greater variation in seasons, which leads to climate change because you'll have more severe winters and more severe summers. So, yeah, you have greater climate variability, climate change. And so, really, if your tilt is greater, you're more tilted towards or you're tilted further away from the sun during the seasons. So, during greater Earth's tilt, you're going to have more intense seasons and overall warmer temperatures, but really it's about the stronger seasons, more intense seasons. And then there's eccentricity, which is the I guess ovalness, how elliptical the orbit of the Earth is. So a perfect circle is non-elliptical; it's just a circle, like this right here. And then a more eccentric orbit looks like an oval, an ellipse. That's like Earth. Now Earth has an elliptical orbit, but it's how elliptical the orbit is changes every, I think it says 100,000 years. And this obviously changes the climate because the closer you are to the sun, the warmer it's going to be, right? So, yeah, and the eccentricity, or how elliptical the Earth's orbit is, tells you if you're closer or further away from the sun, and you also have more extreme seasons because more elliptical orbit means you get closer to the sun, but then on your way back you're further away, as you can see here. I think they call it aphelion and perihelion, which are larger the more elliptical you are. So you get stronger, hotter summers and colder winters, just like in obliquity. Um, and in precession, this is when the Earth changes what season is closest to the sun. So right now, in the northern hemisphere, the Earth is closest to the sun in the winter, and in 22,000 years, it's going to be closest to the sun in the summer, which means that the summer is way hotter in the northern hemisphere than normal, because it's closer to the sun in the summer, right? And it also means the global on average be warmer because the northern hemisphere contains more land, which heats up faster, which means the global average temperature will be higher. So there you go. If the northern hemisphere is hotter, the average global temperature will be higher. It's just how it works because the northern hemisphere has a lot more land than the southern. So there you go. Now let's look at volcanoes and aerosols. So this also includes wildfires, forest fires, which release a lot of aerosols. So volcanoes release it specifically in the form of SO2. So other common aerosols are NOx, CO, VOCs, and black carbon, commonly emitted by coal burning. All of these are from NOx and VOCs and CO are emitted also by gas-powered cars, but sulfur dioxide and black carbon specifically emitted from coal burning, combustion of coal engines, anything that runs on coal. Aerosols are deadly. They cause about 1 million deaths annually. They're very bad, especially in India and China, I think I mentioned. Especially China. They have a lot of industry over there. These aerosols, specifically SO2, is what caused a lot of the acid deposition. Sorry, SO4. So different sulfur, but it's under the SOx acronym, but different kind of sulfate. It caused acid deposition really bad in the United States. And if I bring my pointer back, you can see substantially in this area right over here. In the East Coast, which is where a lot of the people lived at the time. Not much over here, acid deposition, because the populations were lower, but it's where a large concentration of the population existed at the time. And this is where most of the emission of coal combustion occurred. So we had a lot of acid rain, and we actually defeated the acid rain crisis. And it's actually one example we like to use when we discuss climate change solutions. We hope to do the same thing with climate change as we did for the acid deposition problem we had. Also, and there's really sad images in forests in the Appalachian Mountains, which are right here. Appalachians are somewhere over here, like right in the middle of the acid deposition area. Some forests have been totally destroyed by acid rain. It's horrible to see. It's an environmental, ecological disaster. So I didn't mention it, but wildfires. At least I think I mentioned it. A lot of aerosols and CO2. So aerosols are like those things that get caught in you. So examples are like PM 2.5 and PM 10. They're pollutants. They're basically just pollutants. I didn't mention ozone in here, but ozone is also a greenhouse gas. So ozone is a pollutant and a greenhouse gas as well. It's also emitted by vehicles like cars and other reasons. It's what keeps the stratosphere so warm, because the ozone is a good greenhouse gas. Protects us from UV radiation, but not the troposphere. Tropospheric ozone is toxic for the lungs, and it causes climate change. It's a global greenhouse gas. So yeah, wildfires release a lot of CO2 when they burn, and they also release a lot of aerosols. Very bad for the lungs. Can give you lung cancer. Aerosols are just bad. Like I said, they're pollutants. Sulfur dioxide released from volcanoes often blocks out the sun, which is what we see from here. When Krakatoa happened in the 19th century, it brought global temperatures down several degrees Celsius. It caused a nuclear winter type of event, they called it, and it was snowing in like summer in some areas in Europe. I think Mary Shelley even wrote about it or something, but yeah, it was snowing when it shouldn't be. So yeah, volcanoes definitely have an impact on the climate. They have a net cooling effect. So then the next question comes, well, what about the Hungatonga eruption? And, well, um, suffice to say, that actually had a net warming instead of a net cooling, which a lot of people need to bring up. Um, but why is that? Well, it's because it released a lot of water vapor into the stratosphere because it's an underwater volcano. So when this volcano erupted, it pushed a lot of um, water vapor that was down deep in the ocean, went up into the stratosphere. There's so much energy, so much energy. Um, I don't have the article, but it pumped out 50 times, or maybe 50, like 50 times the energy of an atomic bomb. So it was so much energy getting released, flung up into the atmosphere, so high into the atmosphere, went to the stratosphere where it stayed for years. Water vapor usually goes away after a couple weeks by precipitation. It precipitates out. However, water vapor in the stratosphere doesn't precipitate out, and it can exist there for years, potentially years, because it doesn't precipitate out. So, because of that, is the Hungatonga eruption of early 2022 has actually shown to cause some warming in the atmosphere, and it's believed that it has contributed to the warming of 2023 and 2024. So we brought up the solar cycle, and we brought up the ENSO and volcano. So all three of those combined are kind of this perfect storm that has allowed the past couple of years climate to be much warmer than normal. And so it's shown, but these aren't impossible events. Like something like this could always happen again. It's showing that climate change is getting worse than we expected, and faster than we expected. And seeing these last couple of years has shown to us what's really in store with climate change, and certainly something we should be concerned of, I think. First of all, the solar cycle was observed by Galileo a long time ago, I think 17th century, as he used one of the first major telescopes, and he noticed he shouldn't, well, probably a little dangerous, but he didn't know back then. He was looking at the sun, and he noticed the number of spots on the sun was changing. It wasn't always the same. He's like, oh, that's strange. Why does it change? Well, I guess he didn't really know back then, but it actually follows a pattern that he may not have realized. I don't know if he did, but every 11 years, the sun goes through a cycle called the solar cycle, and it varies the number of sunspots that are visible on the sun. And so this is kind of odd, because sunspots are actually cooler spots on the sun, but the greater number of sunspots on the sun, the more active the sun currently is, and the warmer the Earth will be. So, or I shouldn't say the warmer, the larger amount of radiation that the sun is putting out. It's putting out greater energy output. So more solar energy is reaching the Earth than normal, which causes more warming. It affects our energy budget, which we'll talk about the energy budget in a minute. But as you can see, the solar constant, which is what I'm saying about that radiation, increases and decreases with the solar cycle. And this is what warms the Earth during the solar cycle. So right now we're about to reach a solar maximum, which probably is going to look similar to this, because this was a weak one. We're getting a pretty strong solar cycle this year, so it's going to be probably one of the stronger ones like here. And as you can see, it helps warm things. So the reason 2024 and 2023 have been so warm, especially 2024, I think part of it has to do with the solar cycle. Not totally, but that certainly helps. And then you also have ENSO, so we're in El Nino, but I think that's next. So, but that also has to do with the reason 2024 has been so warm. So yeah, solar storms. Yeah, you have more solar storms as well in the solar maximum at the peaks, and that's what causes auroras. That's why I have a little picture of an aurora right here, which auroras are so cool. So I had to put a picture of one right here. But yeah, so we get some cool things with the sun too. You get auroras. So here's ENSO. So the reason I brought this up is in El Nino years, which we're in right now, that is when the average temperature on average in the northern hemisphere is usually a little warmer and drier. Now it varies where you are on the earth, or wetter. I should say wetter. It's not dry. That's La Nina. Wetter and warmer than normal. I think in the winter. But this past year was an El Nino cycle, and that helps warm the earth by a little bit, by a few tenths of a degree. And that solar maximum also helps raise it by a couple tenths of a degree. So that certainly helped lead to the record warming that we've seen in on the Earth. So I think this is the most frequent climate variation on Earth. This happens every few years. Solar maximum, solar cycles every 11 years, and so it stands for El Nino Southern Oscillation. And if you look it up, I'm not going to tell you exactly, but yes, La Nina counts. La Nina is technically the Southern Oscillation, but the person that came up with ENSO didn't realize that they were connected. So that's funny. They didn't know El Nino and La Nina were the same thing, really. They were kind of found out separately, which is really funny. Found out separately. But yeah, it's how global circulation on Earth change and impact seasons temporarily. So as we can see on the right, here what's the El Nino season looks like. This is courtesy of NOAA, by the way. I'm not this cool, I'm not that smart. I didn't make this. This is from NOAA. So this is El Nino year, and this is La Nina. So you can kind of see how the weather patterns change during each one. So yeah. This is why we say in California usually it's wetter during El Nino and not during La Nina, because of kind of what you see here. So in an El Nino year, kind of already talked about this, warmer, and particularly in the winter months is when it kind of starts. And La Ninas are usually longer than El Ninos, actually, turns out. El Ninos usually last less than a year. El Ninos can last consecutive years. And then the other situation that's not El Nino or La Nina, the globe is neutral. And I would say you have about 1 in 3 chance of any one. And like neutral happens probably almost as frequently as these other two. These have been happening a lot. Like we just had La Nina, now we're having El Nino, we're about to have another La Nina. So neutral doesn't actually happen as frequently as you might think. But yeah, there you go. This is a very important cycle. A lot of climate deniers like to use the ENSO cycle and the solar cycle, and even this one, these natural variabilities, to say that the Earth isn't warming as much as we say it is. And a lot of it is because of, these cycles are smaller scale. They're happening in our lifetimes, and we actually see the temperatures changing, varying. So they're saying, well, that's just this cycle, and we'll get into why that's not true. So exactly, why should we worry today? Right? Clearly the Earth's been warmer before, it's been cooler before. So why should we care the speed of the warming? I think I've mentioned this before. We saw the graph where it's skyrocketing. And I mentioned before, natural availability takes tens of thousands, sometimes over 1 million years. I think just like it says right here, a snowball Earth. It takes a very long time to get to those temperatures. Earth's inertia is pretty slow. It's not that fast. And current warming has only happened in the last 150 years. That's the big one. It's the speed. Also, life was very different in those conditions. So first of all, there were mass extinction events. I'm pretty sure I haven't actually pulled up the extinction events map, but I can say with pretty high certainty there were extinction events, like the ones with the dinosaurs. The climate changed substantially from meteors, right? And volcanoes, which we talked about earlier. These events will cause, to block out the sun or reduce the solar constant, which we also saw for the sun. But yeah, they cause extinctions, cold and hot. And we're not used to this sudden change in temperature at all. Humans and all life on Earth. Humans actually adapt better than most life. We're very technologically advanced creatures, but it can be devastating for the surrounding environment and ecology of the world Earth's ecosystems. So just because it doesn't affect us doesn't mean it doesn't affect the rest of the Earth. So it's important that we notice that.